When we look up at the night sky, we perceive stars spread across the canvas of space. We imagine planets moving through voids, light traveling through nothingness. But what if space is not an empty stage, and time not just a ticking clock? What if they are both parts of a deeper structure? A fabric of reality we've only just begun to understand? This concept lies at the heart of Einstein's theory of general relativity, which revolutionized our view of space and time. Instead of treating them as separate entities, Einstein unified them into a single four-dimensional continuum known as space-time. In this model, massive objects don't simply exist within space. They bend it. They warp the geometry of space-time, and that warping is what we perceive as gravity. Picture space-time as a stretched rubber sheet. If you place a bowling ball on it, say a star, the sheet curves. Smaller objects, like planets, follow those curves. They don't feel a force pulling them. They're simply moving along the natural bends in space-time. This elegant insight explained everything from the orbits of planets to the bending of starlight near the sun. It even predicted the existence of gravitational waves, ripples in space-time itself, caused by massive events like black hole mergers, something we've now observed. But the fabric of space-time may be far more complex than a smooth surface. Physicists now suspect it may be quantized at the smallest scales, not continuous, but made of tiny, discrete units, much like pixels in a digital image. This idea is central to the search for a theory of quantum gravity, an elusive framework that would unify general relativity with quantum mechanics. One of the most compelling candidates for this unification is string theory. According to string theory, the fundamental building blocks of the universe are not particles, but tiny vibrating strings of energy. These strings can vibrate at different frequencies, giving rise to the particles we observe: electrons, quarks, photons, and more. But there's a twist. String theory only works if there are more dimensions than we can see. While we live in 3 dimensions of space and 1 of time, string theory suggests there are 10 or even 11 dimensions, most of them curled up at unimaginably small scales. These extra dimensions may help explain some of the deepest puzzles in physics, like why gravity is so much weaker than the other fundamental forces. If gravity is leaking into other dimensions, it might explain why it appears so faint in ours. The existence of hidden dimensions isn't just theoretical. Experiments at facilities like the Large Hadron Collider, LHC, are probing high-energy collisions to detect signs of extra dimensions. While no direct evidence has been found yet, the search continues, and the implications are staggering. If other dimensions exist, they could harbor entire realities, other universes with their own physical laws. This idea gives rise to the multiverse hypothesis, where our universe is just one of countless others. These universes may be separated not by distance, but by dimensions beyond our perception. Some physicists go further, suggesting that space-time itself might be an emergent phenomenon, not fundamental, but a byproduct of quantum entanglement. In this view, space and time arise from the way information is interconnected at the smallest scales. Reality, then, might be less like a solid stage and more like a vast quantum network, a hologram projected from deeper mathematical structures. This idea is supported by the holographic principle, which proposes that all the information contained in a volume of space can be represented on its boundary. It's as if our 3-dimensional universe is a projection of 2-dimensional data, a cosmic illusion with very real consequences. Incredible as it sounds, this principle has gained traction in black hole physics, where it helps resolve the information paradox by suggesting that data is stored on the event horizon. If true, it means that reality as we experience it might be encoded at the edges of our universe. These theories are bold, complex, and still evolving. They challenge our intuitions and force us to reimagine the very nature of existence. But they also hint at something beautiful, that the universe may be deeper, stranger, and more interconnected than we ever imagined. Perhaps we are like fish in a pond, sensing only the ripples on the surface, unaware of the vast ocean of dimensions just beyond our reach. Yet we are beginning to see patterns in the waves, gravitational lenses bending light, quantum entanglement connecting particles across the void, and the persistent hum of the cosmic microwave background reminding us of our fiery origins. In this unfolding mystery, we are both explorers and part of the fabric itself. Our thoughts, our measurements, our questions, they are threads woven into the grand tapestry of space and time. The fabric of reality is not a backdrop, it is the story, and we are still writing it.